So this is section 7.2. And this, people have said, last class, does this get tougher? This seemed to be where my kids struggled a bit more. So that's my way of saying, turn your brains on. Half-life. Turns out radioisotopes decay. And because aside from gamma rays, when it's beta particles or alpha particles, the procedure changed the number of protons. Allison, you were always forming new elements. Carbon-14 turned into nitrogen, for example. It turns out different isotopes decay at different rates. Some very quickly, some phenomenally quickly, like in trillionths of a second. And some incredibly slowly. In fact, one we didn't realize was decaying. We thought it was stable, and it's only been in about the past 20 years or so that we went, holy smokes, it decays. It just decays in a time that's longer than the age of the universe thus far. So what we do, the way we measure how long it takes for them to decay, we determine, here is your word, half-like, Mr. Dueck, this isn't Facebook, half-life of each. Does anybody know what the word half-life means? If I say something has a half-life of 12 hours, what does that mean?
6 hours.
Nope. Nope. Has nothing to do with 6 or 24. If something has a half-life of 12 hours, what you're saying is if you started out with 100 grams, in 12 hours, 50 grams would be left. That's how long it takes for half of it to decay. Or if you started out with 80 grams, in 12 hours, 40 would be left. And in another 12 hours, 20 would be left. And another 12 hours, 10 would be left. Another 12 hours, 5 would be, remember I said you're going to be dividing by 2 an awful lot over and over and over and over and over and over. Half-life says how long does it take for half of the substance to decay? Half of the parent isotope to turn into the daughter isotope. It's the time it takes for 1/2, 1/2. What is that as a percentage? 50% of the atoms decay. And if you have a faster decay, that means you have a shorter half-life. I think it's francium, which is on your periodic table in the first row at the bottom. It has a half-life in the, I think, trillionths of seconds. It decays really, really, really fast. You get it, it's gone. Let's talk about a few. I'm not going to say C14. How would I pronounce that? What's the C stand for? What? Okay, carbon-14 is the radioactive isotope of carbon. All of you have some radioactive carbon-14 in you. And as long as you're alive, you keep replenishing it so that the percentage, Julia, of you that's carbon-14 stays roughly the same. But as soon as you die, that carbon-14 starts to decay, which gives us a way to measure how long it's been since you died. This is how we date objects that are 15,000 years, living objects that were once living, that are 15,000 years old or 20,000 years old. This is how, for example, we've dated some of the mummies in the Egyptian tombs. This is how we know how old some of those pharaoh mummies are. We use carbon-14 dating. So while alive, organisms take in and lose carbon. And what this means, Ryland, is all of you have roughly the same ratio of stable carbon-12 to radioactive carbon-14, and we can measure that. But when an organism dies, it's no longer taking in new carbon, it's just decaying. The carbon-14 continues to decay. So the longer an object has been dead, the less carbon-14 there is. So this can be used to measure how old something is. Like King Tut. but it can only be used to measure objects that were once living. This doesn't help you figure out how old the pyramids are. Oh, but if you found a bunch of objects that were once living inside a room, you might say maybe this room was built around the same time as all the objects that we found in it, maybe. There's a weakness in that argument. Maybe it was already an old, ancient room, and they were just using this to store stuff. Carbon-14 decays into nitrogen. In fact, that's an isotope pair. There are some common isotope pairs. The isotope that you start out with is the parent, while the stable product is called the what isotope? I've used the word, but we haven't written it. Huh? Yeah, daughter isotope. For example, uranium-235, which is the parent, decays into lead-207. I think that's on your formula, on your purple sheet. Yeah? There's I think 5 parent-daughter pairs with half-lives. So do you need to memorize them? No. Do you need to know that they're there so that when I ask you about them, you don't say, I don't know, it's on your sheet? Yep. Is it 5 or 4?
No, but it says lead-206 on the purple sheet.
It says lead-206 on the purple sheet? Is it uranium-235?
Yeah.
Uranium-235 decays? But uranium doesn't, remember, that was the graph I actually showed you a couple of classes ago that had 13 steps. Uranium goes through a lot. But this is the daughter. The problem is lead-207 is not completely stable either. It's going to continue to decay into something else. I think thallium or something. I have to look it up. I haven't memorized these. Didn't need to. They're on my purple sheet. So, this is going to be a written question on your test. Somebody asked me about the test. This would be a great question. Something like this. Suppose you have 12 grams of a radioactive substance, substance X. And you know its half-life is 8 years. So in year 0, how many half-lives have elapsed? That's meant to be really obvious. 0. You're starting with 12. The fraction remaining is 1 out of 1. Percent remaining is 100. After 1 half-life, how many years is that? 8. How many grams would be remaining? 6. As a fraction, how much is remaining? 1/2. As a percent, how much is remaining? What about after 2 half-lives? How many years would that be from when we started? 16. Now, the nice thing is, 2 is a times table most of you are pretty good at, but I'm not going to try and make up nice numbers all the time. In fact, the ones on your sheet, on the purple sheet, have actual half-lives, and they're not convenient to do math with in your head, so you can use a calculator. But this one here with 8 years is pretty easy to do. What will be remaining after 16 years? That's how much of the parent, how much of the daughter would there be? If there's 3 grams left of the parent, how much of it? 9 grams. Because there's another question, I could say how much of the daughter would there be? What fraction is remaining? Half of a half. 1/4. What percentage? Keep going. What if we go with 3 half-lives? How many years is that? 24. How much is left? Sorry? We already got 3 grams. Half of that, which is 1.5. Yes? Fraction remaining? Percent remaining? Oh, by the way, the fraction rate, right? 1/8, right? Multiply the bottom by 2. 25% divided by 2, 12.5? By the way, so 1/8 is the parent, what fraction is the daughter? If 1/8 is the parent, what fraction left is the daughter? 7/8. 7/8. In fact, we could even say this. The ratio would be 1/8 would be the parent, 7/8 would be the daughter. The ratio, if you were doing the research, Allison, you would find a 1:7 ratio of substance X to its daughter stable substance. And then you could use that to work your way backwards. This chart is clear, too much writing, so I'm going to try and, Sage, shorten this, but we're going to use this notion of skipping along. Anyways, some questions we can answer. So after 8 years, how many grams do you have left? What did we say? 6. After 16 years, how many grams do you have left? After 16 years, what fraction of the parent isotope is left? Could you figure out a way to get there without the chart? If you knew it was 2 half-lives, it's 2 times 2, it's 1/4. We'll talk about that. After 16 years, what percent of the parent isotope is left? 25. Ooh, after 24 years, how much of the parent isotope material is there? 1.5 grams. After 24 years, how much of the daughter isotope material must there now be then? Do the math, or use your calculator. Sorry? 10.5, right? If we had 12 grams of stuff, we still have 12 grams of stuff. If 1.5 of it is the original stuff, 10.5 grams must be the daughter isotope. Yes, I did this for Matt. Brainium is a mysterious radioactive substance. Has a half-life of 7 minutes. Similar to your attention span. Never mind. Suppose we start with 60 grams of brainium. All right. Look at the questions. What's the biggest number of minutes the questions talks about? 35. What's one half-life? How many minutes? So how many half-lives to get to 35? I'm going to try, rather than do a big chart, I'm going to try and go like this. Are you ready? There's going to be 1, 2, 3, 4, 5 half-lives. I'm going to use little bouncy arrows. Don't freak out, Tyra. It'll become clear in a second. I just don't want to do that big chart. Too much work. What are we starting with? How many grams, Tyra? How many grams? 60. After 1 half-life, how many left? 30. After 2 half-lives, how many left? Keep going. 7.5. 3.75? Now you need a calculator. I told you guys you need a calculator. So you got a calculator, divide 3.75 by 2. 1.875. Yeah?
How many decimal places do you go?
You know what? I probably won't go more than 3 decimal places. Okay? In fact, if you said 1.88, but anyways, it's a nice decimal, so I'll carry it. Okay. There's my chart. Let's see if just that alone is enough for me to answer any of the questions. What's A ask? After how many minutes? You know what? How many minutes is this 60 at? Trick question. No, it's not set. How many? 0. Then how many? 7. Then 14. Then 21. Then 28. And you can see I'm trying to keep stuff lined up. I'm trying, Allison, to sort of replicate that chart, but with as little writing as possible. 35. So after 14 minutes, how many grams of parent isotope are left? You're right. Say it loud and proud. 15. After 28 minutes, how many grams of parent isotope are left? 3.75. Ooh, after 28 minutes, same amount of time, how much of it is the daughter isotope? How will I figure that out? How will I figure that out? Oh, what did we start with, grand total? 60. How much of the parent is left after 28 minutes? So how can I figure out how much is the daughter? So 60 minus 3.75. I can do that in my head. 60 take away 3 is 57 minus 0.75, 56.25. Double check me. Yeah? I can do math in my head. What's D asking me to find? Not how many grams. What? What fraction? After how many minutes? 35. Okay. Well, it goes like this. 1 over 1, 1 over 2, 1 over 4, 1 over 8. Spot the pattern. What's going to be next? Just the only issue, Julie, start counting from 0, start counting from 1 over 1, start counting from 100%. That's at time 0. What's the next one? You know what? 1 over 32. That's what's left. 31 out of 32, that's the daughter. Oh, and I just answered that. I didn't see E. 31 out of 32. I think that's less work than doing the chart. And it's not that much writing, but it's nice and organized. Where can you make mistakes? Conlon, I strongly encourage you, keep everything nice and lined up. Okay? And don't be scared to number things. It's an easy way to keep track of stuff. And you'll notice by looking at the numbers ahead of time, I was able to figure out how many of these I needed to go. I didn't need to do the loops ahead of time, Tyra. I could have just started and stopped when I got to 35 minutes as well. Oh yeah, turn the page. Suppose a substance has a half-life of 4 hours. These are good test questions. Oh, I like this question. 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 Why did I say that? Did you hear me say it was going to be on the test? Or you just kind of student tends to notice these little hints? Good for you. Okay. Suppose a substance has a half-life of 4 hours. What percent will be left after 1 day? Okay, this one wants me to go with percents. Okay. What percent do I start with? Yump. There's 1 half-life. How many hours is that? 4. You know what? Instead of putting 1 half-life, I'll put a 4H right there because that's less writing. What's left after 4 hours? Have we got to 1 day yet? How many hours is 1 day going to be? Well, let's keep going. How many hours is this now? Not 4. 8. What's left? I can see where we're going with this. How many hours? 12. What's left after 12? 12.5. Yump. 16. What was 12.5 divided by 2? 6.25. What's after 16? 18 hours. What's left? I don't think it's 20 hours. Oh, it is 20 hours. I can't do math, Mr. Dueck. 20 hours. Thank you, Dylan. Candy for you. Pause the video, Mr. Dueck. Give Miss Candy because you always forget. 6.25 divided by 2, 3.125, yeah? And here it is. There's your 24-hour day. What percent will be left? 1.562? Is that right? 562. 5625. So I would take a half mark off for 562 because in science we're going to round off properly. I think it'll be 563 because if there's a 5 next to the 2, you round up. Percent. How could I show that's my final answer with all these numbers? There. That's about minimum work for maximum bang for buck. Is that okay, Sage? Is it? So I use, instead of I start out with the chart and then I just use little loops and I either label them with the number of half-lives, like Ryland I did up here, especially because I noticed the question was asking me a bunch of stuff further down, or if it's just one question, I labeled it with a number of times. And it turns out also, how many half-lives? Count with me. 1, 2, 4-hour half-life, 24-hour day. Could you figure out a way ahead of time that you knew it was 6 half-lives? Yeah. So there's shorter ways to get there, but not shorter enough that I'm going to take the risk of making a mistake, Rachel. It's too easy to be off by 1 half-life. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. Suppose you're analyzing some rock and you find that the parent to daughter isotope in a rock sample is 1 to 7. Now here's what that really means. It means that 1/8 of the rock is parent, 7/8 of the rock is daughter, and that's why the ratio is 1 to 7, because it's 1/8 to 7/8. A lot of students, when they see that 1 to 7, they'll say, oh, it's out of 7. Actually, it's out of 8 if you write it as a fraction. If the half-life of the parent isotope is 550 million years, how old is the rock? So now we're actually doing radioactive dating. By the way, from the purple sheet, which one is 550 million years? What element are we talking about here? There is one on there that's 550 million years, isn't there? Oh, I thought there was. My bad. 700. Okay, never mind. This is a made-up one. You're right. I changed the numbers. Okay. So you're doing research and you're analyzing a particular element. You know it's radioactive. You know it's got a half-life of 550 million years. How old is this rock? What we really need to do here, Allison, is go backwards. Did I say go backwards? Well, let's go backwards. Let's go backwards. What would the previous fraction have been? What would the previous fraction have been? What would the previous fraction have been? Starting. Ding, 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 ding. How many half-lives? Not 4. 3. Count the loops. How many half-lives? 3. How many half-lives? 3. See it? So, what's 1 half-life? How many million years? You know what? It's 1, 2, 3. Can you come up with a good abbreviation for half-lives? I'm going to go capital H, capital L. 3 half-lives times 550 million years is what? Do that one in your head. Fine. It's going to be 1,500, 16. It's going to be, is that right? No? Am I right or not? 550 times 3 is 1,650, is it not? Yes? Now, we would never say that. We would actually say 1.65 billion years. But I would take both answers if this was written, because I'm not testing your math skill, I'm testing your science skill. But what you've just done is you have dated a rock. Some of you say, well, I've dated a rock before, believe me. No, I mean, we're talking about actually the geology. It's like talking to a brick wall. Okay, fine. Right? Strong like a brick, smart like a tractor, something like that. That's how we estimate ages of geological formations. And lo and behold, about 80 years ago, we did this with the Earth. And this is how we've come at our 4.5-ish billion years. You can also get this information, Jaden, in some ways easier, in some ways trickier, using what we call a decay curve. So here is mystery element. On the y-axis, we have percentages. On the x-axis, we have time in billions of years. Hey, looking at this graph, by the way, this is a question they love to throw on the provincial because it's easy to do for multiple choice and it's got lots of pretty graphics and all that. Look at this graph. Can you tell me what the half-life of element X is? What? Okay, drop down to 50%, which is right here. That's when you've used up half of your element, Tyra. You've got 50% left. Read across, drop down. See it? 1.3 billion years. You guys, next class or the class after, are actually going to make up your own decay curve from some fake radioactive popcorn, turns out. So what's the half-life? 1.3 billion years. So what percent would be left after 3.9 billion years? Well, it's tricky to read from the graph. Well, but since I picked that 3.9 intentionally, it's exactly 3 half-lives. What percent is left? 12.5. What fraction is left? 1/8. 12.5. By the way, then, what percent of the daughter isotope would be left after 3.9 billion years? 87.5. Okay, we got a half-life of 1.3 billion years. By looking at your purple data sheet, what's the probable identity of element X? What do you have that has a half-life of around 1.3 billion years? Potassium 40? I don't want to write out potassium. Oh, I got a symbol for potassium. K 40, potassium 40. Before you turn the page, okay, we're going to sketch, if you can, with a different color. Oh, no, actually, you guys don't have black ink, so your blue ink is okay. I'm going to change colors. I'm going to go to red. We're going to sketch, this is the parent isotope. We're going to also sketch the daughter isotope. Now, the daughter isotope, we start with 0. After 1.3 billion years, how much of the daughter is left? 50%. After 2.6 billion years, 1/4 is the parent, so how much is the daughter? 75%. After 3.9 billion years, after the daughter curve sort of looks like a flipped upside down image of the parent curve. When one goes up, the other goes down by exactly the same amount. This would be a decay curve and a growth curve on the same graph. So let's draw an arrow and label it. Oh, wait a minute. From your purple sheet, what is the daughter isotope of potassium 40? Argon is AR? Yeah. I'll put in brackets AR 40. In fact, this is one of the big geological clocks that we use. We call it the potassium 40 clock. You guys don't have to turn the page, do you? I do. Oh, no, I gave you this one as well, yeah? Yeah, I found this one online. So here's a decay curve for carbon-14. Okay? What's the half-life for carbon-14 looking at this decay curve? Joseph?
5,000.
5,000?
Years.
Nope. You'd be do better than that. I actually labeled a point right on the graph. It's more than 5,000.
Oh, 5,730 years?
Yeah. Now, you can only get that accurate because I put that point on the graph. Otherwise, if I hadn't put that point on the graph, absolutely, I would have taken, about 5,000 years. Oh, sorry, define half-life. Geez, define half-life. What is the definition of half-life? The 5,730 should go here. What did we say half-life was? How long it takes for what? Time for half of the parent to decay. And you'll notice, Tyra, half-life graphs, they have this curvy shape, sort of like a elongated Nike symbol or something. Yeah, it's an exponential graph. We use them in math all the time. So, how long is one half-life? 5,730. Check. What percentage remains after one half-life? We can already answer this. After one half-life, by definition, what percent remains? 50, half of it. After two half-lives, 25. After three half-lives, now that's as a percentage, but I also told you, it says use the graph to estimate what would the percentage be after 5,000 years. A little more than half, because it's 5,730. So what's well, let's read across. Let's see, 5,000 years. What do you think? I'd take 55. I'd take 56. I'd take 53. I'd take 54. I would not take 49. I wouldn't take 50. I wouldn't take 60. Between 50 and 60 and close to the middle. You okay with how we got that, Julia? You're alive? Give her an elbow for me, would you please? Wakey, wakey, eggs and bakey. Okay? You okay with how I got that, Julie? Yeah. So what do you think? Around 55%? What about after 10,000 years? So 10,000 years, really close, I think, to what percent? I think pretty close to 30. 15,000 years, yeah, I almost think a little closer to 20 than to 15, like 16 or 17. But if you said 15, I'm going to say 17%-ish. But I'd take 15. I'd take 14. I wouldn't take 10. I wouldn't take 20. Okay. Supposing you're studying an organism in the lab and you know that it only has 40% of its carbon-14 left. How old is it? Here's 40%. How old do you think it is? I'd give you 7,000, 7,500 years, 8,000. I wouldn't give you 4,000. I wouldn't give you 5,000. I wouldn't give you 10,000. But certainly, yeah, between 5 and 10. And it almost looks dead center, yeah? So let's go plus or minus 500 years, maybe. Is that okay? You get the hang of how you read these, right? You're either going to read up and back or across and down. What was the next one? 20%. Dunk. Dunk. Right around there, I think, yeah? Between 10 and 15, is it closer to 10 or closer to 15? Closer to 15? So give me a number between 10 and 15 that's closer to 15. I don't think 12 is closer to 15. If it's between 10 and 15 and closer to 15, I heard it here, I'd take 13. Sure, let's go 13,000 years. Again, plus or minus 1,000 years. We can't be exact. We can be close. 5%. Woo! Around 25, I'd get, yeah, it looks to be really close to 25,000. What if we extended this graph to 50,000 years? How much carbon-14 would be left? Well, it never quite hits zero, but it'd be so close to zero Ti, we couldn't detect it anymore. We don't have the instruments. So when it says, explain why carbon-14 measurements aren't effective if the organism has been dead for more than 50,000 years, we can't detect levels that small. There's essentially none. There is still a few atoms. They never totally vanish, but we're not finding them. Then we need a new technique. Oh, we have other elements with longer half-lives on your purple sheet. So Allison, we might try one of the other ones, looking for that. What percent of that is left in the original object? Now, if it's a living object, it might not have any of those. Then we might look at the soil that we found that object in, because we might say, probably when they buried it, if it was a person, when they buried this, maybe roughly the soil is around the same age. Maybe. Could be longer, could be older. But this is how we do a lot of the archaeological dating. The potassium-40 clock. You know what? I took 2 lessons last time. I might finish this all in one. And then that would give us all class, next class to do okay, we'll be good. In archaeology, if any of you go into that field, or geology, there's something that we call the potassium-40 clock. Potassium-40 on your purple sheet. What is potassium? Well, let's write this down. So not all clocks have hands. Anything that measures the passage of time can be its clock. So potassium-40 decays to form argon-40 with a half-life of, what is it from your purple sheet? 1.3 billion years. It turns out when rock turns to lava, through heat, through plate tectonics getting put back underneath into the earth, all the gases, including argon-40, are driven out. They sort of bubble out, but it's more complicated than that, Cameron, because the rock is liquid, but it's more complicated than that. But it resets the clock back to 0. And then when the rock cools again, the potassium-40 decays to argon-40. And by measuring how much of the argon-40 is left compared to the amount of, we can tell not how old the rock is overall, but we can certainly tell how old it is since it cooled. So here's the potassium-40 clock. In blue, now you guys, I couldn't, whoever I was, I think Rachel, I was saying I would kill for a color photocopier. This is one of the reasons. On you guys, I think it's just 2 graphs, but you can kind of figure out which one's which because they're smooth curves. On mine, it's colored. So the parent and the daughter. When one goes down, the other one goes up because the parent decays into the daughter in exactly the same amount. See it there? So this would be a nice test question, and I think in your homework you'll be asked to do some of this. I'll give you a parent-daughter isotope decay curve, and I'll ask you to age some things to determine the age of certain things. So, why is there no argon-40 present in the molten rock when it solidifies? It's driven out. You can sort of think that it bubbles out, but lava doesn't exactly bubble. It's not, but pretend it sort of does. It's a little more complicated than that, but we're not going to get into it. After many years, argon-40 is present in volcanic rock containing potassium-40, but there was no argon-40 there to begin with. So how did the argon-40 get there? Where did it come from? Yeah. K40 decayed into AR40. What's the length in years of one half-life of potassium-40? On your purple sheet, but you can also see it here. Here's the 50% magic marker where you have this. By the way, it's also where the two graphs intersect because you have the same amount of each. Read down, 1.3 billion years. Suppose a sample of volcanic rock contained 100 nanograms, that's a very small amount, of potassium-40. How many nanograms would be left after? Okay, I've asked for how many nanograms of potassium-40 and how many nanograms of argon-40. Let's draw a little line. We'll put potassium on the left and argon on the right. So after one half-life, you'd have 50 nanograms. Abbreviation for nanograms is lowercase ng. And 50 ng. After two half-lives, how many grams would be left? How many grams of nanograms of argon would there be? 75. After three half-lives, 12.5 and 87.5 nanograms. Let me pause the video for a second. I think I'm going to, first of all, nuke this and nuke this. I think you folks are getting the hang of it. What's your homework? I've given you three things. The first is this one that I called Section 7.1 Assignment 2. This one to me is due Wednesday. And then I've also given you a practice quiz on, it's got 8 nuclear equations where you have to figure out the type of decay, alpha, beta, or gamma, and then balance these equations, which are a little easier than the standard chemical equations. This is also due Wednesday. Last year, I took 2 classes to go through this. This year, I got through the Half-Life lesson in 1 class. So I've given you this. This is going to be due next week, Monday, because next class, we're going to be doing an activity. We're going to mark the take-home quiz, and then I have a Half-Life lab activity for us to do involving popcorn and creating a Half-Life decay graph, which will take most of the class, and then you can also work on this. So we're going to press pause. Pardon me? Oh, thank you. Due next week, Wednesday, because of Family Day. Thank you, Ryland, for pointing out my mistake. Any questions on what you're working on? Okay, let me hit pause on the record thingy.